This is just a note on precise fractional integral. I think most of them may know this topic. Okay. Since my background is the numerical mathematics, so after my graduation from Shanghai University, I started to work on numerical method for fractional partial differential equations. So this is new for me, but it's maybe old for you. Okay. So this talk include the following 4 sections. We first give a very simple, very brief introduction for the precise fractional integral. Then we introduce the corresponding integral transforms. We also present some topics very related to this fractional integral. Okay. So what is the precise fractional integral? It is just a compilation of precise of Riemann fractional integral and Stieltjes integral. Here, if no, those are the one. It's the integral from a to t. It is the f tau, and the d precise tau. It is just the Stieltjes integral. Now we introduce the weak singular kilo like this, and also the gamma function. It is just the Riemann fractional integral. But in the first idea and the literature, there is no condition this on precise t. Those are conditions. But here we add these conditions. I will show why we need this condition. When the fractional derivative induced by this kind of integral is used to equation, you will use the corresponding derivative into the equation. We need this condition. Okay. So several special cases are used below. If precise t equal to t, it is just a very long Riemann fractional integral. This is the summer course book, the thick book. Okay, and if it is a log t, then it is becomes the Adama fractional integral. When Vt equals to e to t, it is potential fractional integral. Why do we introduce this kind of precise t? In general, for the ODE, the solution may have exponential asymptotics. Okay, but what about the non-local problem? Okay, if we introduce this kind of precise of t, it is in the non-local problem. Its solution also have its potential asymptotics. Okay. Now, since this is a combination of a Riemann fractional integral and the precise and the Stieltjes integral, so what is the difference between what is the relationship between the Riemann definition and the precise fractional operator? Have this relation? Okay. We can use this formula and the semi-group property of the Riemann fractional integral. We can get to the semi-group property of the precise fractional integral operators like this. So it can be visually represented in the following picture. You can see, okay. Now we introduce the corresponding integral transform. First, we introduce the Laplace transform. If ft is piecewise continuous on any finite interval of this interval, and has the following precise growth condition like this, we can define this. Okay, we get this. So capital F of S exists and is elliptical in the complex half plane. This so is called the Laplace transform, the precise Laplace transform of function f of t. Then we can define the inverse precise Laplace transform like this. Okay. Analog was considered in this paper. There, precise starts from the origin with the homogeneous condition. Okay, but in fact, there is a survey paper in this journal introduced the Laplace transform. Okay, here we introduce the definition that we don't lead the precise starts from the origin and this homogeneous condition. Okay. Now, according to the definition of Laplace transform, we can define the convolution with respect to precise Laplace transform of given functions f of t and g of t, given like this. This is since precise is a strictly increasing function, so it is the inverse exists. So we have the following theorem. This is the Laplace transform of f of t in the sense of precise, instead of precise, and capital G of S is the Laplace transform of G of t in the sense of precise Laplace transform. Okay, so this is a precise fractional integral. Then its Laplace transform is given like this. Okay. We can introduce another kind of Laplace transform. Why we need to introduce such a kind of Laplace transform? We want to derive the condition, the relation between the Laplace transform and the many transform. Okay, we need another kind of Laplace transform like this. So we have seen a condition on f of t. Now we define the fm of s like this. Here we use a precise s minus precise a instead of s, but we need a condition on the precise of t. So this is called the amended precise Laplace transform. Okay. Then we can define the inverse transform like this. Okay. For the precise function, we since the starting point is a. If a is negative infinity, then we can introduce a Fourier transform. But if a is a finite number, we only consider is a Laplace transform. But Fourier transform and the Laplace transform only consider the asymptotics at the infinity point. Okay. This is another kind of integral transform. It considers the asymptotics at the starting point, and the positive infinity point, 2 point. So this is the asymptotics. Okay. If the function satisfies these conditions, then we can define like this. So this is the many transform. Now we can also introduce the inverse precise many transform like this. Okay. We can also define the convolution response to the precise many transform. Okay, like this. This is the convolution. Okay, this is a many transform of FT and the many transform of GFT. Then the convolution, many transform, then is a typical product of the many transform. Okay. This is a precise fraction integral. This is a manifold. They have this formula. This is formula. Now we introduce the relationship between the amended precise Laplace transform and the precise many transform. This is amended Laplace transform. Okay, Laplace transform. This is the many transform. So there is a very beautiful relationship formula for them. Okay. Now we need to know about the reproducibility of fractional integrals in the research field. In the research field of fractional calculus, the reproducibility of the given function by the fraction integral of another function is more important. Than the existence of the fraction derivative with given function. So we introduce two species. This is the species. I mean that all of the functions in this space can be expressed by this fraction integral instead of psi in the LP space. And this is for psi fraction integral. And another, this is for Riemann fraction integral. So GT can be expressed like this. So what is the difference between the two species? So there is a very useful theory from the book, but before some code, someone gave a very beautiful proof. Okay. So two species are equivalent. Okay. If besides this, if psi is the psi fraction integral of where phi t, f of t, phi of t, and the Riemann fractional integral of phi of t, we have the relation between the phi t and where phi of t have these relations. Okay. Now, different from the integer order calculus. For the integer order calculus, we first introduce a derivative, then integral. But the fractional calculus, fractional integral first, then fractional derivative. So such a kind of a derivative is induced by the precise fraction integral. This is a space of absolutely continuous functions on the interval in the sense of this integer order derivative. So we also impose this condition. So that ft, the fractional derivative with order alpha. Here, alpha is positive, then it means derivative. If minus, if negative, then it means integral. Okay, so this is the fractional precise fraction integral integration first, then integer order derivative in the sense of psi. Okay, but precise fractional derivative operator has no semigroup property. No. If we change the order of integration and differentiation, we get the precise capital fractional derivative. This is a differentiation first, then integration. Okay. This kind of derivative operator has no semigroup property. Okay. So these two kind of derivatives are not equivalent with each other, but they have a following relation. Here, they just expansion in the sense of psi. Okay. In general, from the practical application perspective, psi capital fractional derivative is the preferred choice. I will mention this point later. Okay, why in pure math and physics, psi fractional derivative is used, but in applied mathematics and engineering, we use psi capital fractional derivative. Okay. We show why we need this condition psi t approaches positive infinity as t approaches to positive infinity. Well, this is a psi fractional differential equation. Now this is the equation problem. Has a trivial solution. This, if there is a perturbation on the fractional integral initial value condition, for this kind of equation, we give a fractional initial value condition. Okay. So this is a perturbation like this. So we have this is we can explicitly write out their solution. So this is a beta level function with two parameters. Okay. If low is the condition, so psi t can be bounded, then the beta function can be bounded. This means the trivial solution is always stable. Okay, it's always stable. Then this is obviously realistic. So we need the condition. Now, if the condition is imposed to the definition, then by the symplectical property of beta function, and get lambda negative, then this solution is asymptotically stable. And the state variable decays like this, minus alpha minus 1. Okay. If lambda is 0, then the equilibrium is asymptotically stable too. And the state variable decays like this. Since alpha is less than 1, okay, this is also asymptotically stable. But if lambda is positive, then the solution is unstable. The state variable separates from the equilibrium like this. Okay. Now we consider another case. This is a psi capital fractional differential equation like this. This is also a equation problem. But for this kind of equation, we can get the initial value condition like this, st like this. Okay. But for the above system, we give a fractional integral initial value condition. So something different. Okay. Then we can get a solution like this. Now there is a perturbation in the initial value. Then we get the solution. This is the single parameter beta level function. So we get if low this condition, since psi t is increasing, is strictly increasing, but no bounds, then this function can be bounded. Then the trivial solution is always stable, no matter how much lambda is. This is apparently impractical. So we need the condition. Okay, if the derivative is used to different equation. If you impose the condition, then we can get lambda negative. The solution is symptotically stable, and the state variable decays like this. Here is minus alpha, but in the above case, minus alpha minus 1. Okay. If lambda is 0, then the solution, the equilibrium is stable, but not as symmetrical stable. If lambda positive, then the solution equilibrium is unstable, and it decays, and it's a separation like this. This was, since my background is numerical mathematics, so I'm not a pure math, so I want to give this note on this kind of fractional integral. That's all. Thank you very much.
Thank you very much for a very nice presentation.